Production. For many years, the outstanding performance of the laser technology has made possible many advanced applications in the various fields. Mode locking, a technique used to generate the ultra-short laser pulses with the extremely high peak power. In a laser, mode locking refers to the synchronization of the phases of different longitudinal modes of the laser cavity, resulting in the emission of a train of optical pulses. There are two primary methods of the mode locking, active mode locking and the passive mode locking. Active mode locking, it utilizes the external modulator like the electro-optic modulator to impose high-frequency modulation on the laser beam. Passive mode locking, it relies on the saturable absorber or nonlinear optical element within the laser cavity to self-regulate and form ultra-short laser pulses.
Hi, I'm Husna. For the theoretical analysis, first I'm going to talk about the working principle of THDFL and HDFL. THDFL and HDFL lasers use fiber coupling to introduce light into a thulium-holmium codope or holmium dope fiber respectively. The light undergoes amplification as it passes through the fiber medium. Laser emission is achieved by directing the light through a saturable absorber, which increases the absorption in an excited state. The light then passes through a gain medium, which amplifies the light through stimulated emission. Finally, the laser light is emitted as an output, generating a coherent and focused beam. The HDFL and HDFL lasers are capable of producing high-power, narrow line with pulses. For the working principle of graphene, light is coupled into an erbium dope fiber for amplification. The amplified light passes through a photonic crystal fiber containing a graphene solution. Graphene solution acts as a saturable absorber, selectively absorbing light based on its intensity. The absorption properties of graphene help create a stable pattern of pulses. The mode lock light, consisting of closely spaced pulses, is emitted as a laser system's output.
Next, we move on to the proposed design. We have three designs. First, we have holmium dope fiber laser (HDFL). HDFL are mode-locked laser operating beyond 2 micrometers, offering high peak powers and ultra-fast pulse. And in this figure, the HDFL emits at 970 mW and 2110 nanometer. And in this figure, shows multiple pulse with a pulse period of 87.3 nanosecond at 11.45 MHz repetition rate. Next, we have tunable thulium holmium dope fiber laser (THDFL). So in this figure, THDFL emits at 500 mW and 1996 nanometer, and this figure shows multiple pulse with a pulse period of 90.5 nanosecond at a repetition rate of 11.05 MHz. And lastly, we have the proposed photonic crystal fiber graphene based mode lock EDFL. So in this figure, a 980 nanometer laser diode pumps a 3 meter EDF with a 4 mm core and 1 to 5 mm cladding diameters. The EDF contains 2000 ppm erbium and has negative 21.64 picosecond dispersion at 1550 nanometer.
Hi, I'm Nurul Ain Azlan and I'm going to explain about the result. So basically we chose 3 types of laser design based on 2 research papers. So from the 3 design, we execute all the parameters and list down in a table. So from the table, you can make a comparison to choose which laser that can be used for spectral communication, which is the future purposes. In order to achieve the objective, the laser must be more than 2 micrometer wavelength and have a high peak power. So the table then is break down to each type of the lasers, which is the HDFL, THDFL, and also the graphene PCF. So that each table can explain detail about the relationship between the wavelength towards the period, bandwidth, pulse width, pulse period. And so from the 3 lasers, we can conclude that HDFL is the most suitable to choose for future purposes.
When comparing THDFL, HDFL, and graphene in PCF for designing a mode-lock pulse laser system, several factors should be considered. THDFL offers stable wavelengths and high peak power, making it suitable for applications requiring strong laser pulses. HDFL, on the other hand, provides flexibility in adjusting pulse width and narrower spectral bandwidths, offering precise control over the laser output. However, it has lower peak power compared to THDFL. Graphene in PCF is an approach that integrates graphene into the fiber structure, enabling compact and efficient laser systems. It offers short pulses, high peak powers, and adjustable repetition rates, while maintaining stability. However, it's still in the research phase.
So, as conclusion, our first objective is to design a compact, efficient and stable mode locking pulse laser system was successful. This can be seen when each of the lasers shows short pulse and giving the stable operation. This meets the requirements of compact and efficient mode lock pulse laser system. Furthermore, the second objective is to develop pulse laser that apply with high peak power and adjustable repetition rate while maintaining long-term stability. THDFL demonstrates higher pulse energy and peak power, making it suitable for applications requiring more powerful pulses, while HDFL exhibited similar character. The graphene laser delivers shorter pulse with a lower signal-to-noise ratio. The design met the requirements of a compact and efficient mode locking pulse laser system with high peak power and adjustable repetition while maintaining long-term stability. Hence, the second objective was also achieved.